This is our last content unit before we get to the last unit on labs and lab safety. So acids and bases. So when we're talking about acids and bases, we need to talk about their properties. And so we can look at kind of an example of each, their taste, their touch, conductivity, how they react with metals, and what they do with litmus paper. So lemon juice and vinegar are your acids. Soap and bleach are good examples of bases. So taste. Acids taste sour. Bases taste bitter. So when you add vinegar to a dish, you're adding a little bit of that sourness, that kick to it. So acids burn. If you have any cuts on your fingers, it's going to kind of burn or hurt. That lemon juice will. Where bases tend to be slippery. Now, if you touch bleach, it is slippery. Acids and bases both conduct electricity fairly well, just because there are ions in both of them, which we'll see as we go along. Acids tend to react with metals, bases no. Major exception to that would be sodium hydroxide, which is a strong base, and aluminum have a very violent reaction. But in general, it's acids that react with metals and not the bases. And then litmus paper. If you have red and blue litmus paper, you can go back and forth. The way I like to think of it, and the way I remember it, is that bases begins with a B and blue begins with a B. So when it's blue, it's a base. So the two B's match up. That's how I remember what colors what. But we have pH meters now. We have universal litmus paper, that kind of stuff. So, all right. So another thing that's common is acids will also react with marble and limestone to produce carbon dioxide gas. That's why acid rain is a problem for historic cities like Athens and Rome. Looking at nomenclature. So bases are named like any other ionic compound with a hydroxide. So you got sodium hydroxide, potassium hydroxide, barium hydroxide. Name works the same. Acids are different. Acid names depend on what type of ion you have. If it's just a nonmetal, you say hydroic acid, like hydrochloric acid. If it's an 8, then it's ic. So sulfate would be sulfuric acid, or carbonate is carbonic acid. If it's an ite, has one less oxygen than normal, then it's an us acid, nitrous acid. Most common acids are going to be these two. So like hydrochloric, hydrobromic, hydrofluoric acid. Then we got sulfuric, carbonic, phosphoric, nitric. Those are more common acids right there, just because 8 are more common. All right, defining acids and bases. We've got a couple different ways of doing this. We're going to start with what's known as the Arrhenius definition. So in the Arrhenius definition, an acid is something that has an H ion that it gives off. So when it's dissolved in water, it gives off a hydrogen ion, also known as a proton. And so it'll always be in the front of the formula, like this. If it's somewhere else in the formula, it's not an acid, like CH4. Methane has an H in it, but it doesn't do this. And so it's not an acid. An Arrhenius base is something that contains a hydroxide and gives off the hydroxide ion when it's dissolved in water, sodium hydroxide. Okay. Once again, it's always going to be connected to a metal or ammonium. If it's combined with a nonmetal, then it's not a base. All right, so the Arrhenius definition is useful. However, it is not perfect. There are two major problems with it. There are many acids that are not aqueous solutions. Because the Arrhenius definition said, hey, it gives off a hydrogen ion in solution, or it gives off a base, gives off a hydroxide ion in solution. Well, what about gases? What about powders? What about solids? There are a lot of things that aren't pure aqueous solutions. And then some bases, like ammonia, which is a common base, it doesn't contain a hydroxide ion. So we have to come up with a different definition. Now, these are important, but the Arrhenius definition is still useful. If something meets the definition of the Arrhenius definition, it will also meet the definition that we're moving towards, called Bronsted-Lowry. So instead of saying that it's about a hydrogen ion being given off, we're going to say it's a proton donor. So Bronsted-Lowry is a proton donor. It's giving away the H plus ion. Okay? And then the base is a proton acceptor. What's accepting the hydrogen ion, the proton. So for example, if we look at a reaction, I got HCl and H2O. So look what happens to them as they go from one side to the other. HCl becomes a chloride ion. The H is missing. And then the water goes from being water to gaining an H. It goes H3O plus. And so it gains the H. And we would say this is the acid and this is the base. By the way, H3O plus is known as hydronium. We'll be seeing hydronium a lot over the next couple of lessons. And so hydronium is just water with an extra proton added to it. All right. In contrast, if I look at ammonia and water, the ammonia goes from being NH3 to being NH4. It gained a hydrogen or a proton. And the water went from being H2O to being OH. And so it loses a hydrogen. And so this loses the hydrogen that makes it the acid. This gained the hydrogen that makes it the base. Okay, like I said before, it's not so much giving off this hydroxide ion as it is creating it. All right. Another key thing to know here is that the water is a base in the first reaction and an acid in the second reaction. When a chemical can act like as an acid or a base, it is said to be what we call amphoteric. And so that's the term that's used. This is a very important property of water, which we will get to in more detail later. So when we have something that's called a weak acid or base, so we're going to talk about these more later. It has to do with how they dissociate and that kind of thing. What happens is when you have a weak acid or a base, the reaction doesn't go completely forward. The reaction can also go in reverse. So we have a situation where we have equilibrium involved. And so we will have what we call conjugate acids and bases. So an easy way to think about this is if you remember imaginary numbers or complex numbers in algebra, that you have a conjugate pair. So 3 plus 2i and 3 minus 2i are a conjugate pair. So a lot of times it's written 3 plus or minus 2i. They are a pair, but they are opposites. In the same way, the conjugate and acid bases will be the opposite, therefore the reverse reaction. So looking at this one, I've got a double arrow here showing that it's an equilibrium. So going this way, the HF loses, and so it's the acid. Okay, and the H2O becomes hydronium, it gains, and it's the base. But if I look going backwards, it's the hydronium that loses to go back down to 2, and it's the fluoride ion that gains to go back to being HF. So whatever is the acid on one side will be the conjugate base on the other. And whatever is the base will be the conjugate acid on the other. And so they flip and kind of like this. They end up being a pair that go together, but they are in fact opposite each other. So far we've only looked at very simple acids and bases, very simple reactions. But there are a lot of acids and bases that have more than one hydrogen or hydroxide. And so we've got to take those into account, that when we look at sulfuric acid, it usually gives away one and forms this hydrogen sulfate ion, and then it loses its second to form sulfate. And so it does it in 2 steps. We can classify how many they have by using prefixes. And once again, we're looking at the front of it. Now, polyprotic acids, so diprotic and triprotic acids, the way they work chemically, we can assume they work normal. Mathematically, it gets a little wonky in there at times, but we're not going to worry about that too much. You just need to know that some acids are what we call polyprotic, and it happens in stages. It doesn't happen all at once. So we can look at them. So we would say HCl, we would say is monoprotic. Carbonic acid has 2 hydrogens in the front, it's diprotic. Phosphoric acid has 3 and is triprotic. This is acetic acid, this is acetate. Okay, the only one I'm looking at is this one, because that's the only one that's going to be part of the acid. We're looking at the front. This one, these are not involved in being released ever. They stay part of that acetate ion so they don't leave. And so it's considered monoprotic. All right, so I mentioned weak acids earlier, so let's talk about that real quick. A strong acid is something that fully dissociates or ionizes in water, meaning when you put it in water, it splits up perfectly. 100% goes this way. Really, that should be a one-sided arrow instead of a double, but showing that it only goes this way. So all of this is 100% and 0% of this. A weak acid, on the other hand, does not fully dissociate or ionize in water. So for example, hydrofluoric acid, when you have it in solution, 97.5% stays as HF, and only 2.5% ionizes into the hydrogen ion and the fluoride ion. Okay, it is important to note this. When we say that an acid is a strong acid or a weak acid, we are only referring to how well it dissolves. We are not referring to how dangerous it is, nor are we talking to how concentrated it is. You could have really weak, hydrochloric acid that's not going to hurt anybody because it's so diluted, or you could have concentrated this and it's going to hurt and do damage. But I'd actually rather use this in lab than use this. This stuff scares me a lot. Hydrofluoric acid, if you get it on your skin, it doesn't burn so much, but it will soak through your skin and then dissolve your bones from the inside out. Not something you want to play with. And so even though it is technically considered a weak acid, it is still very dangerous. And so never allow this idea that something is weak acid to make you think that it is safe. We do sometimes, something that's more concentrated is more dangerous, something that's less concentrated is less dangerous, but we still have to be careful. So we got to keep those things in mind. So here's what that actually looks like. So the relative strength of a weak acid is given by Ka or Kb for bases. So they're derived from KEQ, and so they're calculated exactly the same way. So it's going to be products over reactants, just like with KEQ. If there were any coefficients here, there would be exponents over here, just like KEQ. It's calculated exactly the same way. So a strong acid or base would have all of this and none of this. So it would have technically an infinite Ka, an infinitely high Ka. So the higher this is, the higher Ka is, the more of this you're going to have. The smaller Ka is, the more of this you have. So just like we've seen before. So it's important to note that stronger acids will have a weaker conjugate base, and then weaker acids will have stronger conjugate bases. That the strength is also opposite. Not only does the acid become the conjugate base, but then it also, if it's weak, the other one will be stronger. If it's stronger, then the other one will be weaker. And so they are kind of opposite pairs, just like we saw before. So looking at that, so this is oxalic acid. It's relatively strong, -2. Its conjugate is really weak, -13. In contrast, carbonic acid, -7, its conjugate's pretty similar. And then this is a hydrogen sulfide ion. Its sulfide ion is much stronger conjugate base. And so they kind of go in opposite directions, as you see there. And so that's your introduction to acids. We have Arrhenius definition, where it's about giving off the hydrogen ion in a solution or a hydroxide ion in solution. Then we have the Bronsted-Lowry definition, that's about being a proton donor or a proton acceptor, basically looking at hydrogens. So acids and Bronsted-Lowry give away hydrogens, bases accept them or gain them. And then we can have reversible reactions where we have conjugates on the other side, and they're always going to be opposite pairs, where the acid becomes the conjugate base and the base becomes the conjugate acid, and their strength will also switch. Now we'll look at how we measure how much of those ions are present by using what is called pH in the next lesson.